During this lesson on flight warning, we will briefly look at the flight warning system and its components. Then we will examine in detail the three different types of alerts, which are visual, oral, and sensory. The basic purpose of an integrated flight warning system is to prioritize all alerts so as to improve a crew's situational awareness. It achieves this by producing different types and levels of alerts relevant to the stage of flight, thereby ensuring that the crew tackle the warning posing the most immediate threat to safety. Before we understand the details of different types and the different levels of alerts, we will very briefly examine the components that make up the flight warning system. The flight warning system consists of a processing unit, to which we have numerous inputs from various system sources, including engine, airframe, and air data sensors, as well as the ground proximity warning system and the traffic alert and collision avoidance system. Most of the input sources and the associated warnings will be covered in this course, and they will be dealt with in separate lessons. However, warnings for engine and airframe system malfunctions will not be covered as they are dealt with within the power plants and system courses. Having very briefly discussed the flight warning system and its components, we will now examine in detail the three different types of warnings that are given to flight crew. The first of these are visual alerts, and there are actually three levels of visual alert. The first and highest is warnings or level A alerts, which appear in red and must attract the crew's attention in sufficient time to take immediate action. The second level is cautions or level B alerts, which appear in amber or yellow and require immediate crew alertness with possible future action. The third level is advisories or level C alerts, which appear in any other colour than red and require crew alertness. Unlike the previous alerts, there are no actions to be completed. Depending on the aircraft type, visual alerts will be depicted in one of two ways, either on electronic screens, as we have already shown, or as lights and/or flags, which is normal on older aeroplanes. Master warning and caution lights, also known as attention getters, are also provided for each pilot to attract their attention to problems that require their immediate attention, and located so as to be clearly visible during a normal instrument scan. In older aeroplane types, these are accompanied by a master warnings panel, where the warnings are placed in a rational order. Having looked at visual alerts, we will now consider audible warnings. An audible warning is mandatory if a pilot needs to take control of the aeroplane, and this can take the form of sounds or a synthetic voice, or a combination of both. As you can imagine, there are numerous types of these alerts, and we will just mention a few out of interest. Boeing aeroplanes have bells, which accompany fire warnings, and a whaler accompanies autopilot disconnect. On Airbus aircraft, a continuous repetitive chime accompanies all level 3 alerts, and a cavalry charge sound is used for autopilot disconnects. In both types of aeroplanes, synthetic voices are used for traffic alert and collision avoidance systems.
Monitor vertical speed.
And ground proximity warning systems.
Wind shear, wind shear, wind shear.
Finally, we consider sensory warnings. The prime example of a sensory warning is the stall warning system. This causes the control column to vibrate. In some aeroplanes, it also pushes the control column forward as a stick push, which initiates a change in pitch of the aeroplane. This is the end of the flight warning system lesson, and you should now understand the different levels of alert and the different ways a crew can be alerted to both internal and external dangers. You should also be able to understand the basic makeup of a typical flight warning system and the various inputs and outputs required for the system to work. In this lesson, we will look at the altitude alert system, during which we will cover the different height ranges, the indications on approaching and deviating from an assigned altitude, the basic components, and EU OPS regulations. The altitude alert system is designed to warn pilots when they are approaching or deviating from the selected altitude. The two major manufacturers, Airbus and Boeing, use different height bands in their alerting systems. The Boeing height band is between 300 and 900 feet. The Airbus height band is between 250 and 750 feet. For the rest of this lesson, we will concentrate on the Boeing heights. So let's look at a typical climb profile. As the aeroplane passes through 900 feet before the assigned altitude, the altitude alert lights illuminate and to momentary toned sounds. On modern displays, this includes a white box around the altitude. As the aeroplane passes through 300 feet to go, the altitude alert light goes out and the white box disappears. If the aircraft should then deviate more than 300 feet from the assigned altitude, the altitude alert light will start to flash, and an amber box is drawn around the altitude, and there is a momentary tone sounded. When the aeroplane goes above 900 feet or descends back to less than 300 feet above the assigned altitude, then the warnings are extinguished. The main component required in a typical system is the altitude alert module. The system also requires information on barometric altitude from the air data computer and the selected altitude from the main control panel. Output from the altitude alert module is then sent to the altitude alert lights, caution lights, engine indicating and crew alerting system, aural warning speakers, and the altimeter. The system is inhibited in flight whenever the glide slope is captured or landing flaps are selected with the gear down. EU OPS requires an aeroplane to be equipped with an altitude alerting system if it is a turbine-equipped aeroplane weighing more than 5,700 kilograms or has more than 9 seats. All turbojet aeroplanes must have an altitude alerting system. The altitude alerting system must be capable of alerting the crew on approaching the pre-selected altitude. The crew must be alerted with at least an aural signal when deviating above or below the pre-selected altitude. During this lesson, you have learnt the different height ranges between Airbus and Boeing aircraft. Also covered was the system reaction to approaching an assigned altitude and deviating from the assigned altitude. Finally, we looked at the components in a typical system, when the system is inhibited, and the EU OPS requirements. In this lesson, we will be covering speed warnings. Included in this will be overspeed and stall warnings. The purpose of the overspeed warning system is to alert the flight crew if the airspeed exceeds the VMO, MMO limits calculated by the air data computer, where VMO is the maximum indicated airspeed and MMO is the maximum Mach number. When we enter an overspeed situation with an electronic system, the following events occur. A clacker is sounded, and the red master warning lights illuminate. and the overspeed message is displayed on the EICAS upper display. The warning cannot be cancelled by pressing the red master warning light and will continue until the crew slows the aeroplane. The overspeed warning light obtains its input from the air data computers via the flight warning system. It has a test facility which can only be used on the ground and checks the oral warning. In the event of system failure, the crew receive no warning if the maximum speed is exceeded. The maximum allowable airspeed is shown either on the airspeed indicator by means of a barber's pole or on an airspeed tape on the primary flight display. Initially, during the climb, VMO is the limiting speed and is indicated by the barber's pole. As the aeroplane climbs from 24,000 to 29,000 feet, then MMO becomes the limiting factor, and this is manifested by the barber's pole reducing in value. The reason it does this is that as altitude increases, when climbing at a constant indicated airspeed, MMO, when expressed as an indicated airspeed, decreases. We will now look at the opposite end of the speed scale and the stall warning system. The purpose of the stall warning system is to warn the crew of an impending stall. It does so when the aircraft approaches the stalling angle of attack, dependent on the current speed and configuration of the aircraft. The simplest system consists of a hinged vane type sensor positioned on the leading edge of the wing and protruding into the airflow. This sort of system is fitted to several types of small aeroplane. In normal level flight, the airflow maintains the vane in line with the relative airflow. As the angle of attack increases, the airflow meets the leading edge at an ever-increasing angle and causes the vane to be deflected. When this deflection reaches a preset value, a switch is made and an oral warning is sounded. Regulations stipulate that in large aeroplanes, the stall warning system must activate before the stall speed by an amount greater than either 5 knots or 5% of calibrated airspeed. It must continue to work until the angle of attack is reduced to at least the point where the stall warning was initiated. The warnings can be in the form of visual warnings, sensory warnings, such as stick shakers, which are fitted to the majority of traditional type aeroplanes, and audible warnings.
Stall, stall, stall.
Most aeroplanes tend to use a combination of these indications, and more modern aeroplanes use the visual and audio indications as their stall warning system.
Stall, stall, stall.
We now move on to the stall protection system. The basic difference between this and the stall warning system is that at the onset of stall protection, providing it has not been isolated, it cannot be overridden, whereas a stall warning system can be. In traditional aeroplanes, stall protection takes the form of a stick push, which physically moves the control column forward, initiating a reduction in the angle of attack. If we look at this graph for a typical fly-by-wire aeroplane, its protection starts at alpha protection, where alpha is the angle of attack. At this point, even if the pilot is demanding full up elevator, the system will only provide a proportion of the actual demand. As alpha continues to increase and reaches alpha floor, the thrust levers are selected to take-off go-around thrust to safeguard the aeroplane. We are now going to look at the typical components required for a stall warning protection system to function. If we look at the inputs required, we need to know the angle of attack, which is provided by a sensor, which we will be looking at in more detail in the next part of this lesson. The positions of flaps and slats affect the pitch of the aeroplane, and therefore the system requires that information. Airspeed is another requirement, and is supplied from the air data computer. The amount of power on the aircraft is also a factor, as the power on stall speed is higher than the power off stall speed. The stall warning system is inhibited on the ground, and so we need an input from the weight on wheels microswitch. We will now look at the outputs from the stall warning module, and as already stated, aeroplanes will have a combination of indications. First is the stick shaker motor, which is fitted to more traditional aeroplanes. Then we have visual warnings, which come as master warning lights, and written warnings on electronic screens, and audible warnings in the form of synthetic voices and oral warnings. We also have an output to the angle of attack indicator. There is also a test facility, which can only be used on the ground to test the system. A stall protection system differs from the stall warning system only in that it is triggered at a later stage than the stall warning, and it has different outputs. In a traditional aeroplane, we have the stick push, whereas in more modern aeroplanes, we have an output to the auto throttles, which move them to take-off go-around thrust. As previously mentioned during the components phase, we are now going to learn about the angle of attack sensing probes. They are positioned on each side of the forward fuselage with two basic types in use: a vane type or a conical slotted probe. Both are protected against ice formation by a heater. The vane detector is a counterbalanced aerodynamic vane, which positions the rotor of a synchro, which is used to measure the subsequent angle. The conical probe protrudes from the side of the aircraft into the airflow. The probe is attached to a paddle wheel inside the transmitter housing and has two vents set into it, which feed either side of the paddle wheel. As the aeroplane rotates, the airflow strikes the probe differently, and this causes a pressure differential within the paddle. The paddle and probe then move so as to rebalance the pressure. The probe, or vane, drives an electric pickup which is then sent to the stall warning module and can be displayed on an angle of attack indicator if fitted. During this lesson, you have learnt about high-speed and low-speed aerodynamic warnings. The first thing to be looked at was the overspeed warning and the indication provided to crews. Then you were shown the stall warning system and the different ways this is indicated to a crew dependent on how modern an aeroplane you are operating. Next was the stall protection system, how it differs from stall warning, and the different ways it is presented to the crew dependent on the age of the aeroplane. Finally, we considered the components of a typical stall warning system, including the types of probes that are used to input the angle of attack to the stall warning protection system. During this lesson on the Ground Proximity Warning System, or GPWS, we will have a look at its history, its modes of operation, and the indications associated with these modes. We will look at enhanced GPWS, the actions required on receipt of a GPWS warning, and the components in a typical system. Then we will have a very brief look at the runway awareness and advisory system. The ground proximity warning system is a means of alerting crews to the danger of flying into terrain. GPWS was introduced in the mid-1970s to prevent controlled flight into terrain accidents resulting from crew errors or distractions. Prior to its introduction, there were approximately 3 to 4 controlled flight into terrain events per year, killing hundreds of people. After GPWS was introduced, there was a major reduction in the number of controlled flight into terrain accidents. GPWS has a height operating band of between 50 and 2,450 feet actual height above the surface, and automatically selects the correct mode of operation. The crew are informed by means of visual and audible warning signals when the aircraft's proximity to terrain poses a threat.
Pull up! Pull up!
We will now look at the individual modes of operating, starting with Mode 1. This gives us protection against excessive barometric descent rate. It has 2 boundaries and is independent of aircraft configuration. Penetration of the first boundary generates an oral alert, which is repeated every second and a half.
Sink rate! Sink rate!
Penetration of the second boundary generates a visual and audible warning until the rate of descent has been corrected.
Pull up! Pull up!
Mode 2 has inputs from radio altitude rate of change, Mach number, barometric altitude, and aircraft configuration. It also has 2 boundaries. Crossing into the first boundary causes an oral alert.
Terrain! Terrain!
The caution boundary is so small that almost instantaneously it will be followed by a visual and audible warning.
Pull up! Pull up!
After leaving the pull-up area, the audible alert will again be heard while in the terrain segment.
Terrain! Terrain!
If both boundaries are penetrated in the landing configuration, then only the repeating audible alert message is heard. This is repeated every second and a half.
Terrain! Terrain!
As speed increases to between 220 knots, or Mach 0.35, and 310 knots, or Mach 0.45, with undercarriage up, the highest radio altitude at which Mode 2 operates is increased to 2,450 feet. This higher portion is inhibited with the flap override switch in the flap override position. Mode 3 provides an alert if a descent is made during the initial climb or go-around. Mode 3 is effective between 50 and 700 feet radio altitude and generates the alert when the aeroplane has descended by 10% of the existing radio altitude. It is not armed during the approach until below 200 feet radio altitude. The oral alert is repeated every second and a half until the flight condition is corrected.
Don't sink! Don't sink!
Mode 4A is protection against unsafe terrain clearance when the undercarriage is not down. The system is armed after takeoff and after passing through 700 feet radio altitude. When the aeroplane subsequently descends below 500 feet radio altitude and at a speed of below 220 knots, or Mach 0.35, then the oral alert "too low gear" is heard and repeated every second and a half with the visual indication "pull up."
Too low gear! Too low gear!
With an increase of speed to above 220 knots, or Mach 0.35, the boundary is increased to 1,000 feet radio altitude, and the oral alert changes to "too low terrain." It is also repeated every second and a half.
Too low terrain! Too low terrain!
For Mode 4B to activate, the undercarriage needs to be in the down position and flaps not in the landing position. If the aeroplane then descends below about 250 feet at a speed of less than 190 knots, or Mach 0.28, then the oral alert "too low flaps" is sounded along with the visual pull-up warning.
Too low flaps. Too low flaps.
If the aeroplane's speed is above 190 knots, or Mach decimal 28, then the height range is increased to 1,000 feet, and the oral alert becomes too low terrain.
Too low terrain. Too low terrain.
In both mode 4A and 4B, the message is repeated every second and a half until the condition has been corrected. The too low gear alert takes priority over the too low flaps, and both can be inhibited by use of the flap gear inhibit switch. A Mode 5 alert is issued when the aeroplane descends more than 1.3 dots below the glide slope. Mode 5 is armed when a valid ILS signal is being received by the captain's glide slope receiver and the radio altitude is below 1,000 feet. There are two areas of alert, soft and loud. In both areas, the alert is a repeated glide slope call and the illumination of the below glide slope light.
Glide slope. Glide slope. Glide slope.
In both areas, the voice message repetition rate increases as the glide slope deviation increases.
Glide slope. Glide slope. Glide slope.
In the loud alerting area, the voice message amplitude is increased.
Glide slope. Glide slope.
Mode 5 can be cancelled or inhibited by pressing either pilot's below glide slope light while below 1,000 feet radio altitude. It will rearm again on climbing above 1,000 feet radio altitude. Modes 1 to 4 oral alerts have priority over Mode 5 alerts. However, both pull-up and below glide slope lights could be illuminated at the same time. Mode 6A operates between 50 and 1,000 feet and provides the crew with an oral warning if the aeroplane descends below the minimum decision height as set on the captain's radio altimeter. The oral alert minimums sounds only once and will be rearmed when the radio altitude becomes greater than that selected.
Minimums.
Mode 6B adds two further safety features to the GPWS system and consists of height callouts on approach and bank angle alert.
500. 100. 50. 40. 30. 10.
Bank angle is to warn crews of excessive roll rates. The bank angle limit reduces the closer to the ground the aeroplane is because of reduced wingtip and engine pod clearance.
Bank angle. Bank angle.
Mode 7, which has priority over all other modes, provides the crew with visual and oral alerts and warnings when entering a potential wind shear area. To achieve this, it requires inputs from ground speed, airspeed, barometric height, rate of descent, and radio altitude. The system reacts to the onset of wind shear conditions. This allows crews to initiate the escape maneuvers earlier, giving them a greater chance of avoiding a potential accident.
Wind shear. Wind shear. Wind shear.
If an aeroplane continues into the wind shear area, then visual and oral warnings are issued. The red wind shear warning illuminates, and wind shear, wind shear, wind shear is announced.
Wind shear. Wind shear. Wind shear.
We will now take a brief look at enhanced GPWS, sometimes called eGPWS. The reason this system was introduced is because the original GPWS could not anticipate terrain ahead of the aeroplane, and consequently, when approaching a hill rising rapidly from the terrain, it would not produce a Mode 2 warning. What was introduced was enhanced GPWS, and this includes a world terrain database and is sometimes known as a Terrain Awareness and Warning System, TAWS. To enable this system to function, it has to know the position of the aeroplane, so is dependent on the accuracy of the aeroplane's navigation equipment. The system provides both visual and audible warnings of terrain. Visual warnings are displayed either on the weather radar, navigation display, or on the warning system's own planned position indicator. The terrain is displayed using the colours green, yellow and red. When approaching terrain ahead, the terrain colour changes from green to solid yellow and an oral alert is given.
Caution, terrain, caution, terrain.
If the aeroplane continues towards the obstacle, then the terrain colour changes from yellow to red and an audible warning is given.
Terrain, terrain. Roll up.
In addition, a terrain clearance floor has been developed around all airports to warn against potential premature descent on non-precision approaches like VOR NDB approaches. We will now look at the actions required on receipt of a GPWS EGPWS warning.
Roll up.
The action should be immediate and positive and is to roll the wings level and initiate a maximum gradient climb, which should be maintained until the aircraft is above the minimum safe altitude for the part of the route being operated. Once established in the climb, then and only then should the crew look into the reason for the warning and verify the aeroplane's actual position. The only circumstances when a climb to safe altitude may be discontinued are when the cause of the warning has been positively identified or the warning ceases. The pilot must not deactivate the system unless told to do so by the operations manual. The airline operator should be informed of all warnings, even nuisance or false alarms, so that remedial action can be taken so as to maintain confidence in the GPWS system. The two times when the GPWS EGPWS would need to be inhibited occur during the approach phase. These are either if the flap gear positions are known to be non-standard, or if the crew are flying in an approach without regard to the glide slope. We will now look at the components in a typical GPWS EGPWS system, and we start with the brains of the system in the central processing unit. Into the central processing unit are various inputs from the radio altimeter for actual height above the ground, Mach meter, air data computer for all the barometric information, glide path deviation, undercarriage, and flap positions, and finally, input from the navigation system. The central processing unit takes the inputs and then produces either an alert, this is a caution generated by the system, or a warning, which is a command generated by the system. This is then sent back to the necessary output, including the master indicator, visual warning, and audio warning. The final part to GPWS is the runway awareness and advisory system, which was introduced to help reduce the number of runway incursions. The system has a database of all airport layouts, so combined with an accurate navigation positioning system, like GPS, it enables the system to know where the aeroplane is in relation to runways and taxiways. It helps improve a crew's situational awareness when in the vicinity of an airport by issuing various oral alerts during taxi, takeoff, approach and landing. During this lesson, you have seen the different modes of operation of the Ground Proximity Warning System, GPWS, when they apply, and the different configurations required to trigger a warning or alert. You may wish to take some time to study the table before continuing. You were also shown the reason that the Enhanced Ground Proximity Warning System, sometimes known as the Terrain Awareness System, TAWS, was introduced. Next, you saw the required actions to be taken in the event of a GPS warning or alert, and the components of a typical GPWS system. During this lesson, we are going to look at the Traffic Collision and Avoidance System, TCAS, which is also known as the Airborne Collision Avoidance System, EICAS. We will look at the equipment required, how it is operated, the indications, and action to be taken in the event of a traffic advisory or a resolution advisory.
Descend, descend.
TCAS does not guarantee a specific separation from other aeroplanes, but does inform crews of traffic in the vicinity of their aeroplane and gives vertical vectors to avoid other contacts. It does this by adapting the transponder system to not only reply to ground radar interrogation, but also to other aeroplanes. For TCAS to see another aeroplane, it must have at least a mode alpha transponder fitted. Without that, TCAS is blind to other traffic. With mode alpha, you get range and bearing information. In addition, mode Charlie gives height information. So let's take a closer look at the equipment fitted in the aeroplane. The transponder is a transmitter, receiver and computer in one combined unit. For the system to transmit and receive, we require aerials which are fitted to the top and bottom of the aeroplane fuselage. In addition, with version 7 of TCAS 2, which is the EICAS standard system, we also incorporate Mode S, which incorporates a discrete data link between aeroplanes. We obviously need a control panel to input the mode alpha frequency, turn the system on, select the range, and select resolution advisories off, as in certain situations the aeroplane will not have the performance to carry out the vertical maneuvers the system might demand. We also require a means of displaying the traffic seen by the system. This can take the form of a dedicated display, or it can be incorporated into the vertical speed indicator, the navigation display, or the primary flight display. Now look at how TCAS works and the indications presented to the crew. TCAS works on the secondary radar principle using the normal transponder frequencies of 1030 and 1090 MHz and can deal with numerous threats at the same time. Using this principle, it creates two protective three-dimensional bubbles around the aircraft, labelled TA and RA on the diagram. These are based on the time to reach the closest point of contact, which is called a TAW. The limit time is different depending on aircraft altitude, which is linked to a sensitivity level, and the planned separation value is between 300 and 600 feet, increasing to 700 feet above flight level 420. If any aeroplane enters the first bubble, then a traffic advisory is displayed to the crew in the form of an amber circle. In this example, the target aeroplane is depicted as -04, which is 400 feet below. As well as the visual warning, a verbal warning is also given, as this is a potential collision threat.
Traffic, traffic.
If the aeroplane continues on this track and enters the second bubble, then a resolution advisory is generated. The symbol changes from an amber circle to a red square, and either a preventative advisory or a corrective advisory is issued in the vertical plane, instructing you to climb or descend. A preventative advisory is where no risk of collision exists unless either aeroplane changes its vertical profile. In this case, the instruction is to monitor vertical speed.
Monitor vertical speed.
A corrective advisory is where a collision risk exists and a maneuver is necessary to avert it.
Descend, descend.
The limitation of the system is that the aeroplanes could be given similar avoidance actions, and collision may not be avoided. So with version 7 of TCAS 2, Mode S was introduced, which is a discrete data transfer between the aeroplanes and ensures that they are given different vertical instructions. As well as traffic and resolution advisories, the system also displays other traffic and proximate traffic. Other traffic represents transponder-equipped aircraft within the selected range and in a relative height band of plus or minus 2,700 feet, and is indicated by a hollow cyan diamond. Proximate traffic is traffic within 6 nautical miles and within a height range of plus or minus 1,200 feet, and displayed by a solid cyan diamond. The symbols used on this particular example are +10 and an up arrow. This shows a contact 1,000 feet above and climbing at a rate of 500 feet per minute or more. The least reliable information displayed from TCAS is the bearing, so crews should not try to interpret tracks or anticipate the system, as they could make the situation worse. This is why all resolution advisories are given in the vertical plane. Occasionally, a target can be displayed without bearing information. These are displayed at the bottom of the screen, and up to 2 targets can be displayed in this way. The first figure is the range to the contact in nautical miles, and the second the height, including minus for below and plus for above, and the arrow signifying a climb or a descent of 500 feet per minute or more.
Increase climb, increase climb.
So far, for simplicity, we have shown the TCAS information on the vertical speed indicator, but on most aeroplanes the contact information is displayed on the main navigation display. The climb descent resolution advisory information is displayed on the primary flight display vertical speed scale using a red band. In this example, the system is demanding a descent rate in excess of 1,500 feet per minute. There are times when the aircraft is not going to be able to follow a full resolution advisory, and so there are various inputs into the system which restricts TCAS resolution advisories. An input from the radio altimeter restricts resolution advisories from issuing the increased descent instruction below 1,450 feet. At 1,000 feet, no resolution advisories are produced, and below 400 feet, no traffic advisories are produced. Where the aircraft's performance is limited, that is at height, or with gear or flaps deployed, climb and increase climb resolution advisories are inhibited. On receipt of a traffic advisory, crew should try to locate the target aeroplane and be prepared to respond to a resolution advisory if the situation changes. If the aircraft cannot be located and gives further cause for concern, then crew should seek advice from air traffic control.
Traffic, 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 traffic.
If TCAS issues a resolution re-advisory, crews are required to respond to the TCAS command immediately. Resolution re-advisories override ATC instructions. During the maneuver, crew should inform air traffic of their actions by using the TCAS instruction. For example, TCAS climb or TCAS descent.
Climb, climb.
On completion of a TCAS maneuver, the aeroplane should be returned to its assigned flight level, and air traffic should be informed of this. From this lesson, you know what the components of a typical TCAS system are, how TCAS is operated, and the indications associated with the system. You also learned under what circumstances the TCAS system would be inhibited, and the actions required from a crew during traffic and resolution advisories.
Climb, climb,
During this lesson, we will be looking at recording equipment which consists of two items that can be supplied as a combined unit, but normally are installed as separate items. They are the Flight Data Recorder, FDR, and the Cockpit Voice Recorder, CVR. Both are commonly called black boxes and are fitted to all commercial aeroplanes to record flight data and cockpit audio and to preserve the information so that it can be analysed in the event of an accident. They are painted red or orange to aid in their location, positioned near the tail area of the aeroplane to help deal with excessive G-forces, and designed to withstand fire, shock, heat, and water damage. Firstly, we will look at the flight data recorder equipment, its recorded parameters, and EU OPS requirements. Then we will look at the same things for the cockpit voice recorder. One component in a typical flight data recording system is a digital recording system which records at least the last 10 or 25 hours of aircraft data. Connected to the flight data recorder is a flight data interface unit which collects and processes all input parameters. Those inputs include the main and additional parameters. The next component is a 3-axis linear accelerator which measures acceleration in all 3 planes. In addition, there are 2 control panels. Firstly, the flight recorder control panel. This has a ground control switch which is latched in the auto position and will automatically turn the system on when airborne or on the ground with one engine running and for up to 5 minutes after engine shutdown. On selects the system on outside these parameters. The other control panel has an event marker switch which allows crews to mark an event for further investigation on return to base. Most modern digital flight recorders actually record hundreds of inputs, but the main inputs required for aeroplanes above 5,700 kilograms consist of either time or a relative time count, pressure altitude, indicated airspeed, heading, pitch and roll attitude, normal acceleration, radio transmission keying, thrust or power on each engine, thrust lever position including reverse thrust, configuration of lift and drag devices, total or outside air temperature, use of automatic flight control systems, and the angle of attack. Additional parameters, mandatory for aeroplanes above 27,000 kilograms, which are recorded, include the positions of primary flight controls and trim, radio altitude and navigation information displayed to the crew, cockpit warnings, and landing gear position. If you wish to see any of the images enlarged again, just click on them. EU OPS requires aeroplanes that are registered on or after 1st of April 1998 and having a maximum takeoff weight of 5,700 kilograms or less to be fitted with a digital flight data recorder that will record a minimum of the last 10 hours of operation. Aeroplanes with more than 9 seats that are multi-engine turbine powered, or aeroplanes weighing more than 5,700 kilograms require a digital flight data recorder capable of recording a minimum of the last 25 hours of its operation. The flight data recorder must start automatically before the aeroplane moves under its own power, and stop automatically after it is incapable of moving under its own power. The flight data recorder must have a device, such as a sonar locator beacon, to assist in locating it in water. Aeroplanes of 5,700 kilograms or less may be fitted with a combined flight data recorder and cockpit voice recorder. An aeroplane may be dispatched with an inoperative flight data recorder, provided that it is not reasonably practical to repair or replace it before the flight. The aeroplane does not exceed 8 further consecutive flights. Not more than 72 hours have elapsed since the unserviceability, and any cockpit voice recorder required to be carried is operative unless it is a combined unit. We will now look at the cockpit voice recorder, which is basically a tape recorder with a control panel which incorporates a monitor display and an area microphone. The control panel has a test button which initiates a built-in test, and this is indicated either by an LED or the monitor needle moving into the green segment along with a 600 or 800 Hz tone that can be heard via the headset jack. When the auto on switch is selected to auto, the cockpit voice recorder starts recording from when the first engine is started and then until 5 minutes after the last engine is shut down on the ground. When selected to on, it will record outside the above parameters, switching back to auto when the first engine is started. The erase button will only erase the recording under the following circumstances. The aircraft is on the ground with the parking brake set and the engine shut down, and the erase switch must be held selected for a minimum of 2 seconds. On some control panels, like the one on the left, an area microphone is incorporated. Others use separate microphones around the cockpit. The voice recorder is a standard magnetic tape recorder which is required to provide a minimum of 30 minutes of 4-channel parallel recording. The system records any radio transmissions from the captain's, first officer's and observer's position. On one channel, we have the interphone from the captain's, first officer's and observer's position. The next channel records public announcements made from the captain's, first officer's and observer's position. The next channel records all navigation or approach aids selected by the crew. Finally, the area microphone records any conversations or noises heard within the cockpit environment. All aeroplanes registered before 1st of April 1998 and either weighing more than 5,700 kilograms or with more than 9 seats and weighing 5,700 kilograms or less are required to have a cockpit voice recorder capable of recording the last 30 minutes of operation. Aeroplanes registered on or after that date, being multi-engine turbine powered and having more than 9 seats or a maximum takeoff weight of above 5,700 kilograms, need to record a minimum of the last 2 hours of operation. Aeroplanes of 5,700 kilograms or less and registered on or after the 1st of April 1998 need to record a minimum of 30 minutes of operation. The recorder must record as a minimum all the parameters as stated earlier in this lesson. It must start to record prior to the aeroplane moving under its own power until the aeroplane is unable to move under its own power after shutdown. The cockpit voice recorder must have a device to assist in being located in water. An aeroplane may be dispatched with an inoperative cockpit voice recorder, provided that it is not reasonably practical to repair or replace it before flight, the aeroplane does not exceed 8 further consecutive flights, not more than 72 hours have elapsed since the unserviceability, and any flight data recorder required to be carried is operative, unless it is a combined unit. During this lesson, you have learned about the flight data recorder and the cockpit voice recorder. You have looked at the components in both the flight data recorder and cockpit voice recorder systems. Then you were shown the parameters that the flight data recorder and cockpit voice recorder record. Finally, you were shown the EUOPS requirements for both the flight data recorder and the cockpit voice recorder.